pleasure, and I feel really privileged to be here today with you and to be the part of this conference. And the question is right now, what is the feasible place to stand? So maybe that's the best way. So, okay, so today during this talk, I would like to briefly introduce you the history of the AI, currently where we are standing with the AI and where we are heading to, actually. And of course, I will try to omit all the math details because that would not be so interesting for you, I believe. So it will be a really very, I would say, friendly presentation. So first of all, we know that AI, in generally speaking, actually the dawns of the AI can be found or could have been found in the Second World War when actually some predecessors of the AI started to emerge. And then, of course, gradually AI started to progress. There are actually two things, or two milestones I would like to mention, which were the first milestone. It was the Deep Blue, which was the typical representative of the so-called artificial narrow intelligence. Most of you guys who used to play, for example, in the 90s, real-time strategies on first personal computers, most of this AI was actually driven by this narrow intelligence. So it was basically the intelligence, AI or artificial intelligence, designed just for this particular purpose and with no generalization capabilities. And the first landmark of the, I would say, of this narrow AI was the Deep Blue computer or I would say framework, which challenged the Kasparov in the game of chess. Kasparov at that time, he was the chess master, world master, actually, and it was the first time when actually AI challenged the master of any table game. Of course, at that time, it was, again, you know, this so-called narrow intelligence because the evaluation function, which was driving the turns of the Deep Blue, was proposed completely by the human. Actually, it consists of many features like safetiness of the king, number of pieces on board, but everything was fine-tuned by the human. So, and at the end, I think Deep Blue marked the first victory, 3.5 to 2.5, and Kasparov was really upset about that. He blamed that the Deep Blue, it was not actually the AI, it was like a brute force approach and stuff like that. But anyways, this was the first time when the AI beat the chess master. A chess world master like Kasparov, of course. Second milestone I would like to mention is the year 2016, where the project or startup DeepMind challenged the Lee Sedol. He was the Go world master. Go was extremely complex, or still is extremely complex, because compared to the chess, it has much more in terms of number of positions on board, it's much more complex. When talking about the number of states that could happen in this game, this number is more than atoms in the universe. So it was really unthinkable to even think about proposing AI agent beating Lee Sedol, for example. So in this time, Deep Blue, the guys, they proposed to use, for the first time, very interesting, I would say, phenomena. It was called reinforcement learning, together with the more conventional data set learning. So first of all, at the first stage, the agent was trained on the massive data set, corpus of data set consisting of the previous games of the experts, but that was later fine-tuned by the reinforcement learning concept. Reinforcement learning is a very complex thing, but long story short, it's like having the child who receives some feedback, either positive or negative. For example, when we are the kids, of course, we still remember when we fall down on the ground, it really gives you a lot of pain. So it's some sort of, say, negative feedback. Of course, when you did something good, actually, or fine, your parents gave you some sweet chocolate or whatever, so it was like more positive feedback. And this is some, I would say, reward, which was driving the way how you interacted with the environment. So here in this case, they implemented reinforcement learning. So the agent, in this case AlphaGo, was trained against each other, against its copy, and trying to get some information about this game. So for the first time, it started to be really innovative in that sense, compared to, for example, compared to the Deep Blue. So that was another very important and really splendid moment in AI. And of course, this massive data set training and reinforcement learning is currently empowering large language models. Most of you are quite familiar with ChatGPT, I think, or Gemini from Google, or Anthropic. And actually, all these systems are based on really massive training, or really huge training on internet scale data, and later fine-tuned by the reinforcement learning concept. So that was actually just a brief mention of the milestones we experienced in the past when talking about the AI. Right now, what are the jagged frontiers of modern AI? The jagged intelligence was proposed by Andrej Karpathy. Actually, he used to study in Bratislava, but also in Košice, one of the most famous colleagues in AI from Slovakia, together with Michal Valko, of course. So he claims that, unfortunately, these days, large language models, they suffer from the jagged intelligence. Jagged intelligence means that in some tasks, LLMs, or large language models, they really excels, like math Olympiads, programming, and so on. But on the other hand, they completely fail in very, very, very easy tasks. For example, this screenshot is taken from Anthropic. Is 9.11 bigger than 9.9? Of course, he's very optimistic, or actually he gives us a really false decision, because he claims that 9.11 is bigger than 9.1, which is not the case, of course. Second thing I want to mention is very recently GPT released GPT-5, and there was another, I would say, tricky problem with GPT-5, because when asking how many times does the letter B appear in Blueberry, of course it's obvious we have only 2 occurrences of B, but actually GPT-5 answers we have 3 times letter B in that word, so which is not correct again. So the question is, how can we rely on LLM, especially in the business context, when we can, from time to time, face these kind of things? And on the top of that, also, another problem which we are currently facing when trying to deploy AI systems in the practice is the fact that they were not trained by its definition, because of its definition, they were not trained on giving you some correct answers for very complex things, like planning and optimization. In the computer science, it's called constraint satisfaction problems. For example, like I need to drive across town, find a route that minimizes fuel consumption. It's typical, like use case for the navigation, or schedule a meeting for 2 people with complex overlapping calendars. Or, for example, when you are in Schiphol, you wouldn't handle the operation of Schiphol to LLM when tens of aircrafts are landing and taking off at the same time. So that's the question, what is the boundary? To what certain extent we can trust LLMs, and where we need to dedicate that hard work to some other external tool? So how can we move right now forward with LLMs? That's a good question. So actually the basic concept, which is called agentic AI, is to divide the tasks. First task, or first part of the task, is to understand your prompt, your query. Actually, LLM is perfectly fine with that. So actually, you can ask LLMs to do something, and LLM will, of course, understand or grasp the information you gave to him, and it will generate some data form consisting of all the things you need. And later, the JSON, for example, structured data format, will be sent to some other external tool who will handle the computation of your task, like calculator or some external APIs or planner or whatsoever. By doing that, we can leverage the upsides of both aspects, like understanding the context, and letting for example, complex tasks to be computed at the external tool or the external server. So very, very simple pseudocode, how it looks like. So first of all, we of course ask a very complex question. Then this LLM orchestrator will decompose that prompt or your question to some particular subtasks. Yes? And then it will call some external tools like calculators, APIs, as I said, and will send the dedicated data to that external tool. And then the tool, of course, need to process those data, and LLM will receive the data, synthesize them, and give you the feedback. That's actually this concept is called reasoning plus acting, right? So because we can do that in this loop, and we can, for example, to refine the results and stuff like that. But of course, each calling of the API, each processing of your query costs some money, so we have to be very frugal with our queries. So another problem, so right now we know how to process the data. The problem with LLMs, of course, is the fact that they can't or they do not have your data available. For example, your confident data and confidential data, of course, and you don't want to, expose those data to the public. So you need to build up your own agents who can process your data. So how can we deal with that? That's the problem right now. One solution how to overcome this problem is the so-called retrieval augmented generation, which is actually the framework invited a couple of years ago. But before we go to this RAG, I would like just to very shortly inform you how are actually being your PDF files processed by the RAG or by LLM in general. So first of all, of course, we have some PDF on SharePoint, of course, of Microsoft. You use Microsoft, you've got all your data located on SharePoint. We need to process those data, those PDF files, and we need to transform those PDF files to the text, raw text. And then another action we need to chunk those data. We don't want to work with the large documents. We want to rather work with small parts of the docs, of the text, which could be also overlapping, just to retrieve the information and the context. So we are, unfortunately, the pointer is not working, I think, or it's very small. So we are somewhere here. So we have the text files, chunks, and then we need to tokenize them. Because tokenization is the process where your words are actually broken to some smaller words, like these are called tokens, like subwords, going down even to the alphabet, to the letter of the alphabet, for example. And then those tokens are being processed and moved to the vector domain. So instead of the text, instead of the words, we are working with the vectors. The reason for that, there are many reasons for that, why to deal with the vectors rather than with the tokens, but this is not so important right now. Just keep in mind that we are working with the vectors. This is very, very simple example how it looks like, of course, in the vector space, although in the LLMs we are talking about the hyperdimensional vector space, more than 1,000 coordinates, but here we have just for the readability, we have only 3D space, of course. And after moving to the vector space, we see that the words which have very similar semantic meaning are located or clustered together, like huge or large, right? Or searching or retrieval. That's very important. So it means that the vectors which brings very similar meaning are grouped together. And those words which are not relevant to that cluster are more distant, okay? And so this is basically why our LLMs are working. So that's the most important thing, vector space. So right now we know that all the words are, or all the text, or your text or chunks are being transformed to the vectors. So the question is, how can we work with RAG, as I said? RAG, there's a very nice example how the RAG works. It's like an open book exam. I believe many of you in the past undertook the open book exam, which means that you enroll to your exam, you go to the class, and you can use whatever you want. All the books you need, you can use them to process the answer for your teacher. The same is being done with the RAG. Okay, so you ask about some information you want to retrieve from your RAG system. Our LLM will then search in your vectorized database, and the search is basically being implemented in that way that we compare the vector distance between your question, which is also vectorized, your question, and the chunks you have in your RAG. And the RAG will find the chunks with the closest distance, which means they resemble or they bear the very, very close information to your question. And then, after taking that chunk, LLM synthesize that and give you the answer. Basically, actually what we can see right now, so this is a very simple toy example. So who discovered penicillin? We can have two chunks in our RAG. Penicillin was discovered by Alexander Fleming in 1928 and so on. And the second was Howard Florey and Ernst Boring Chain later developed these methods to mass produce the penicillin. In this case, the cosine similarity was equal to 0.84, and in the latter case, it was 0.82, which means semantically they are very close to each other, and since LLMs operate or have probabilistic nature, it can happen very easily that the LLM will choose the second one, because it's actually all about the probability. And in that case, it would be, the answer would be like penicillin was discovered by Florey and Chen during Second World War, which is actually not correct, of course. This is so-called hallucination or fabricating the outputs, which we need to cope with somehow. First thing how to overcome the problem of the hallucination is the concept called re-ranker, which actually extend the functionality of the RAG. So, first of all, as I said, we need to find the chunks with the largest cosine similarity. They can be, for example, top 25. Okay, so we've got the chunks, top 25 chunks taken from our RAG, from our vectorized database, and then we know that we can have some troubles with the fabrication of the results. So what we actually can implement is the concept called re-ranker. Yeah, re-ranker takes all these chunks, and together with your user prompt, and re-ranker basically is another transformer, which gives you some relevant score, because it processes simultaneously all the RAGs, particular chunks, and at the same time also the user prompt together jointly, and it can give you some relevance to your between your query and the particular chunks taken from your RAG. I will show later the impact of the existence of the re-ranker. But second thing which starts to emerge these days is also the concept of the graph-based RAG. Graph-based RAG is very nice thing because it actually creates some ontology based on the graph structure. So you just need to let, for example, LLM process all your data, and LLM will be capable of creating some graph where you can have some entities and the relations between those entities. Of course, there are some inherent drawbacks of having this graph-based RAG, but somehow in certain situations it can be very useful. So again, let's go back to our toy example. So who discovered penicillin, right? Again, we have our two famous answers from our RAG, but after re-rankering, after processing the chunks and our query at the same time by the transformer, in this case it was BERT transformer, as we can see, re-ranker score is extremely high right now for the correct answer, and for the second answer is quite low, which means that most of the time LLM will pick up this one, yes, and will have correct answer. Still, again, from time to time, due to its heuristics, we can get some false results, of course. Another thing, so right now we talked about RAG, re-ranker, and graph-based RAG. Another solution, how can we empower our proactive chatbots in the enterprises, for example, is, as I said, to deploy some kind of business tools and let the LLM to interact with those business tools. So LLM will process your input, and thanks to its reasoning capabilities, it will ask your external servers, external databases, for example, through API calls to get those information, and later that information will be processed by the LLM. So it's extremely powerful right now to combine the enterprise tools like, for example, SharePoint from Microsoft together with the LLMs. And putting it all together, so we have RAG, graph-based RAG, re-ranker, we have external tools. I just showcased a couple of use cases where we can use latest LLM cutting-edge technology like LLM together with the external tools. For example, customer support automation. So in the RAG, we can put all our past ticket data. So RAG, it would be deployed with all the information you process in the past from your customers. And the tools, and you will also allow the LLM to execute API calls to the customer relation management database. And the bot would be capable of fully resolving common issues, which are currently processed by the first layer support, of course. And second thing is, for example, if you are a data scientist, you can save to the RAG the company's database schema and the key performance, KPIs you are using commonly, and the tool can write and execute SQL queries to your database. And by doing that, just by writing down the prompt, you will get all the necessary data you want, and the whole process could be completely automatized. So actually the output or the result would be pretty obvious. So it will lead to the reduction of the manual work, which is actually being seen right now or being witnessed right now on the market, where, for example, demand for the first or second layer support of the programmers is not more needed to that extent as in the past. Okay, so and right now, since I'm running out of time, my vision, how the vision looks like actually in our case, or actually, I mean, in our opinion, actually, instead of having some master agent like we have right now, like GPT-5, we will have more lightweight models that could actually communicate with each other. So it will be more like multi-agent system. Right now we have single agent system. So we have, for example, GPT-5, which somehow delegates the work to the external tools. In the future, there will be more like lightweight models, which will be capable of interacting and communicating with each other. And there will be also some critic, which will assess the answers from the LLMs. And if it identifies some problems, it will inform one of these agents to correct the answer and will ask to refine the output, for example. So it will be more like multi-agent system instead of single agent system, which we have right now. Thank you for your attention. So I made it in time. So thank you.